Welcome, brilliant minds, to another deep dive.
Hello, everyone. Today, we're plunging into questions that, well, they really stretch the imagination, don't they? Challenging our understanding of reality itself.
Absolutely. We often get questions that push us, to explore new frontiers, and today's comes from a really curious listener at Resmisathish780.
Ah, yes. They reached out after our deep dive on temporal distortion, which they enjoyed.
That's right, they said, I watched your last episode where you made mention to Ninchi B. Lang, PhD's theory of quantum gravity. Could you tell us more about that theory?
And we thought, yes, absolutely we can. So we'll revisit some of his groundbreaking ideas about time and gravity first.
And then, crucially, we're going to dive even deeper into a truly revolutionary concept that aims to unify our understanding of the whole universe.
Yeah, this isn't just abstract physics we're talking about. It gets to the heart of what we think we know about everything.
From the tiniest particles right up to the grandest cosmic structures.
So our mission today is to unpack these complex ideas, pull out the core insights, and hopefully make sense of how they could fundamentally reshape our cosmic perspective.
Prepare yourself, because we're exploring concepts where the universe behaves in ways you might never have imagined. We're aiming to give you that shortcut to being well-informed on some pretty huge questions in physics. Hashtag #TimeTagI. Revisiting Ninchi B. Lang, PhD's Cosmic Insights. Okay, so let's start by revisiting the work of Ninchi B. Lang, PhD, specifically his timescape theory.
Right. For those who joined us on that previous journey, you'll remember it offered a really radical reinterpretation of cosmic acceleration.
Which is a huge deal in cosmology, traditionally the standard model, lambda CDM.
Lambda CDM, that's the one. It basically assumes a uniform, smoothly expanding universe. It's built on what's called the FLRW model.
FLRW, Friedman, Lemaitre, Robertson, Walker.
Exactly. It treats the universe as perfectly homogeneous and isotropic, same everywhere, same in all directions on large scales.
And that assumption, the FLRW model, it led to this massive discovery back in the 90s, right?
Yeah, monumental. The universe's expansion isn't slowing down like everyone expected because of gravity pulling things back together.
No, it's speeding up.
It's accelerating, which was totally unexpected. And this acceleration was then attributed to this mysterious thing called dark energy.
A concept that really shook everything up, got its discoverers a Nobel Prize.
Absolutely. But here's where Ninchi B. Lang throws down a challenge. Is this cosmic acceleration actually real?
Or could it be like an illusion, a trick of our cosmic stopwatches?
Precisely. He asks the fundamental question, is the universe genuinely speeding up? Or is the way time flows messing with our measurements on these huge scales?
So his premise, the core of timescape theory, is no single universal clock.
No universal clock. Time runs at different speeds depending on where you are in the cosmic structure.
So faster in empty voids.
Where gravity is weak, yeah.
Yeah.
And slower in the dense regions like the galaxy filaments and clusters where we live.
Because gravity is stronger there.
Right. And this isn't just, wild speculation. It's really rooted in Einstein's general relativity.
Just pushing its implications further, applying it to the real lumpy universe.
Exactly, instead of that idealized, smooth FLRW model.
And he argued that the cosmological data we have, the CMB, supernovae, BAO,
A cosmic microwave background, distant exploding stars, baryon acoustic oscillations. Yeah, all the big ones.
that data isn't necessarily wrong, is it?
No, not wrong. But he proposed it's been misinterpreted because we keep looking at it through the lens of lambda CDM.
Which assumes that smooth, uniform geometry.
Right. So the standard model itself kind of forces a certain interpretation onto the data. And the timescape model, dark energy. It isn't a real thing.
Not a new force, not some exotic substance.
No. Ninchi B. Lang saw it more as a placeholder, an effective term maybe, or like you hear physicists sometimes call it a fudge factor.
Okay.
It's something you put in the standard equations to make them match what we observe, but it doesn't explain why.
So it becomes more like a description of what happens on average.
Yeah, phenomenological model. It reflects the average behavior of these big structures, the voids and walls across cosmic scales. It's not some intrinsic property of space-time itself.
It emerges from the lumpiness and the different clock speeds.
That's the idea. It's an emergent property.
And this approach, it actually goes way back, doesn't it, to ideas Einstein himself grappled with, like Mach's principle.
Oh, absolutely. Let's really dig into that for a second. Ernst Mach, back in the 19th century.
Physicist and philosopher.
Right. He had this idea about inertia. Newton thought inertia was absolute, tied to some fixed absolute space.
But Mach said, no, it's relational.
Completely relational. An object's resistance to being pushed, its inertia, depends entirely on its relationship to everything else in the universe.
Yeah.
All the distant stars, galaxies, everything.
Wow. So the resistance I feel pushing something is connected to galaxies billions of light years away?
That was Mach's radical idea. He used Newton's spinning bucket analogy. Newton said the water climbs the sides because the bucket's spinning relative to absolute space.
But Mach flipped it.
He flipped it. He said the water climbs because of its motion relative to the bucket and relative to all the distant matter in the universe.
So if the universe spun around a still bucket?
Mach argued the water would still climb the sides because the relative motion is what matters.
Okay, I think I get that. And Einstein loved this.
He was deeply fascinated by it. It fit perfectly with his view of space-time as this dynamic web, not just a fixed background. He wanted to link gravity and inertia to the distribution of matter and energy.
But he couldn't quite get it fully into general relativity?
He struggled with it. GR incorporated some aspects, but didn't completely nail Mach's vision. It's sometimes allowed for mathematically possible, but, weird solutions.
Like Gödel's rotating universe, time travel and stuff.
Exactly. Possible in the math, but didn't seem to match reality.
So what Ninchebe Lang's timescape model tries to do is take that Machian idea and ground it better.
Yeah, embed it properly in our modern understanding of the cosmos. He introduces this cosmological equivalence principle, which is designed specifically to handle these large-scale structures, the lumps, and crucially, to rule out those strange, unphysical solutions like Gödel's universe.
So it makes the relational idea work with the actual lumpy universe we see.
Pretty much, letting the structure dictate the dynamics.
Which brings us back to time dilation, but on a huge scale.
Yeah.
Cosmic scale gravitational time dilation.
Right, we know time dilation is real. GPS satellites prove it every day.
Their clocks tick faster than ours on Earth because they're further from Earth's gravity. It's tiny, but crucial.
Absolutely crucial for GPS to work. And Timescape just takes that same principle, mass warps space-time, slows down time nearby, and applies it to the biggest things there are.
The cosmic web. These huge voids, almost empty.
Hundreds of millions of light years across, very low mass density.
And the dense bits, filaments, clusters, walls where we live, much higher density.
So following Einstein, clocks in those voids with less mass-warping space-time should tick faster.
Faster than clocks like ours, here in the dense walls where gravity's stronger.
Exactly. And we're not talking tiny GPS differences now.
No, because the scale is just immense.
Colossal. It's the cumulative effect across these structures, spanning a huge chunk of the observable universe. The density differences are massive, creating this pervasive difference in clock rates everywhere.
Driven just by how matter is distributed.
Yep. And our observations. When we look out with telescopes, we're looking back in time.
And the light we see today from distant galaxies.
It's traveled through regions where time has been flowing at different rates for billions of years.
And that difference gets imprinted on the light.
That differential flow, that cosmic time slip, it subtly affects what we see.
Okay, now this is where it gets really mind-bending, right? How this differential timing makes it look like there's acceleration.
This is the absolute core of the timescape argument, how it potentially solves the dark energy puzzle without needing dark energy.
Because the standard model, lambda CDM, assumes that smooth, uniform universe, FLRW metric.
Same expansion everywhere, same clock rate everywhere, global uniformity. But we know the universe isn't perfectly smooth.
Einstein's equations are local, aren't they? They describe curvature locally.
Exactly. Applying them globally to a lumpy universe using the smooth FLRW model. It's an approximation. And Ninchebe Lang argued it might be too much of one.
Okay, so Timescape embraces the lumpiness.
Fully embraces it. Highlights that voids dominate the volume of the universe. Something like 59% of the cosmos is void.
Wow.
Now here's a thought experiment. Imagine you're a hypothetical volume average observer, just floating in a typical void.
Okay.
You'd actually see the universe decelerating, gravity slowing things down, like you'd intuitively expect.
Makes sense, but we're not in a void.
That's the kicker. We are not volume average observers. We live in a galaxy in a cluster in a filament. Our cosmic address is heavily biased towards a dense region.
A region of higher density, where clocks run slower.
Right. Slower clocks here, faster clocks out there in the voids. So when we interpret observations like those distant supernovae appearing dimmer than expected,
from our slow clock perspective,
but using a model, FLRW, that assumes everyone's clock ticks at the same universal average rate.
the difference in clock rates gets mistaken for something else.
It gets misinterpreted as acceleration. It makes it look like the universe is expanding faster than it should be.
So you're saying it's an artifact of comparing our local slow clock measurement to a model assuming a universal average clock.
That's the timescape claim.
Yeah.
The universe might actually be decelerating on average, just like gravity would suggest.
Yeah.
But our biased viewpoint, our specific location, makes it look like it's accelerating.
So the apparent cosmic acceleration isn't a mystery force.
It's a perspective effect, a consequence of comparing observations from our clock rate to a model that assumes a different universal rate.
Which leads to this idea of the statistical Copernican principle.
Yeah, another step in cosmic humility, isn't it? First, Copernicus says we're not the center of the universe spatially.
And now Ninchby Lang says our clocks aren't even average.
Exactly. We're biased observers not just in space, but in time, too. Our location in a dense wall fundamentally affects our measurement of the whole universe when we use a uniform model. And that bias, he argues, explains the acceleration without needing dark energy.
Okay. And that connects to the idea of finite infinity. Sounds like a contradiction.
It does. Ninchby Lang borrows the term from George Ellis. It's not literally infinite space. It refers to a specific large cosmological scale, like a boundary.
A boundary around.
Around local structures, like our local group of galaxies, Milky Way, Andromeda, etc., that have become gravitationally bound. Within this region, cosmic expansion has basically stopped. Local gravity won.
Right. We're not expanding away from Andromeda. We're actually heading towards it.
Exactly. We're bound together. That defines our local finite infinity. But beyond that scale, out in the voids, expansion continues.
And this boundary is important
because it defines where the differential expansion and clock rates become most relevant for interpreting certain things. The faster expansion and faster clocks in the voids beyond our finite infinity compared to our slower clocks within it.
It creates an effect.
Yeah, it mimics a velocity boost for us. Like we're moving faster than we really are.
And that relates to the CMB dipole, the hot and cold spots in the cosmic microwave background.
Directly. The standard interpretation is that the CMB looks slightly hotter one way, cooler the other, because our whole local group is zooming along at 600 kilometers per second relative to the CMB rest frame.
But in timescape, maybe we don't need that actual motion.
Maybe not. The CMB dipole could be an apparent motion effect, an illusion caused by these differential clock rates and expansion rates across that finite infinity boundary.
Wow. So our perceived motion through the cosmos might just be an artifact of time flowing differently elsewhere.
It's a potential explanation within timescape. Looking out from our slower region into the faster expanding voids creates an effect that looks like we're moving fast, even if we're relatively still compared to the universe's average matter frame.
It's a fascinating alternative to needing this huge, peculiar velocity for our entire galactic neighborhood.
It really is. And this whole foundational shift, thinking about gravity, maybe not as a force, but as tied to this temporal flow, it's profound. It hints at something deeper, more unified. And it sets the stage perfectly for tackling quantum gravity.
So if time itself holds such power, shaping our view of cosmic expansion, what does that mean for gravity itself? We usually think of it as a force, but these ideas push us somewhere else entirely.
You've absolutely hit the nail on the head. The traditional view, gravity is one of the four fundamental forces. Newton explained it as action at a distance. Einstein described it as space-time curvature.
Right. Newton himself was bothered by action at a distance, wasn't he? He called it a great absurdity. He couldn't explain how it worked.
Exactly. He described that it worked incredibly well, but not the mechanism. Then Einstein comes along with general relativity, completely revolutionizing things. Gravity isn't a force pulling things.
It's objects following the curves in space-time, the bowling ball on the rubber sheet analogy.
That's the one. Mass and energy warp space-time, and objects follow the straightest possible paths, geodesics, through that curved space.
But even GR isn't the final word, right? It breaks down with quantum mechanics.
Notoriously incompatible. Try to combine them, especially at extreme energies like the Big Bang or inside a black hole singularity, and the mass just goes haywire. Infinities pop up everywhere.
And then there's the graviton mystery, the particle that's supposed to carry gravity.
The hypothetical carrier particle, yeah. Analogous to the photon for electromagnetism. But we've never found it. Maybe it's just too weak to detect. Maybe it doesn't exist in that simple form. It's a big missing piece.
Okay, so this brings us to the really radical part. Ninchby Lang's notes on temporal mechanics. His idea is gravity isn't fundamental.
Not a fundamental force, no. It's an emergent property of the flow of time itself.
Whoa. Okay, unpack that.
Imagine this. We're all constantly moving through time, Basically, the speed of light, just in the temporal direction. Now, imagine that flow of time isn't uniform. It gets warped, distorted by mass and energy.
So it's not that gravity warps time.
It's that the warping of time causes gravity. It flips the cause and effect.
That's a subtle but huge difference.
It is. He used a teapot analogy. Teapot floating in empty space, stationary.
Oh.
It's moving straight up the time axis on a space-time diagram.
Right.
Now bring in Earth. Earth warps space-time, especially the time dimension near it. So time flows slower, closer to Earth.
Okay.
The teapot's path on that space-time diagram now curves. It curves towards Earth because time flows slower there. It's essentially pulled towards slower time.
Pulled towards slower time. That explains why things fall.
Exactly. They're naturally moving towards regions where time flows slower. It also explains gravitational time. Dilation, time does flow slower near mass. We've measured it.
Crucial for GPS, like we said.
And it explains why light bends. Light has energy, and that energy is affected by the curvature of time, too. It follows the path towards slower time.
So it unifies all these things, falling objects, time dilation, light bending, under one mechanism, the differential flow of time.
That's the elegance of it. And notice, you don't need a graviton anymore. Gravity isn't a force needing a carrier particle. It's just a consequence of the geometry of time itself.
This shift, gravity as a manifestation of temporal flow, it really does hint at something deeper, a more unified picture. And it paves the way for the next big step, right? A quantum theory of gravity.
It's the perfect segue. Because while Ninschi B. Lang offered these incredible insights, the hunt for a complete theory of quantum gravity merging relativity and quantum mechanics seamlessly is still the holy grail.
And recently, there's been a significant development, a breakthrough that tackles many of the same fundamental questions, but maybe from a different angle.
Indeed. Springer Nature recently published a book, Trans-Planckian Physics and Inflation, by quantum gravity scientist Kenzie Hamada. It's the result of over 20 years of work.
Okay.
And the theory itself is titled Renormalizable and Background-Independent Quantum Gravity. It's potentially, well, a scientific revolution in the making.
Okay, renormalizable and background-independent quantum gravity. Let's break that down. What problems does this theory aim to solve? Singularities must be high on the list.
Top of the list. Those points of infinite density in black holes and the Big Bang where physics just stops making sense.
The traditional view sees them as unavoidable in GR.
Hamada's view. They're probably artifacts. Signs that GR is incomplete. It lacks a kind of floor, a limit to how much space-time can curve.
This is modified GR proposes space-time has elasticity.
Dynamic elastic properties, yeah. Almost like a non-Newtonian fluid like Oobleck. As energy and curvature ramp up, space-time gets harder, less elastic.
Preventing it from collapsing infinitely.
Exactly.
Yeah.
Mathematically, this means adding new terms to Einstein's equations, specifically terms depending on the square of the curvature.
Okay, squared terms.
These are tiny at normal scale, so we don't notice them. But at extreme curvatures, they dominate.
And the result? No singularity.
Collapse stops at a finite, incredibly high curvature. You get an exotic object instead. Maybe the size of an atomic nucleus, but colossal density and curvature. And it's describable by known physics. No breakdown.
And for the early universe?
Same idea.
Yeah.
Not a singularity, but a similar superdense object, balanced. A quantum fluctuation broke the balance, released huge stiffness energy, inflated the universe.
Which sounds like the big bounce idea.
It naturally supports it, yes. The key takeaway is these curved, squared terms are an elegant fix for singularities without breaking everything else.
What about the ghost particle problem? That sounds bad.
It is a major headache. Quantizing gravity with those same curvature-squared terms often implies weird energy that resists negative gravitational energy.
Leading to ghost particles.
Theoretical particles with negative gravity. Never seen, and they'd make systems unstable, potentially creating infinite energy from nothing. Big problems.
So how does Hamada solve this?
He introduces something called a dark particle. But crucially, it's not a classical particle like an electron.
What is it then?
He describes it as a twisted, fluctuating piece of space-time itself.
Okay, hold on. A fluctuating piece of space-time itself. That sounds remarkably similar to where Ninschi B. Lang's ideas were pointing.
Doesn't it? If gravity emerges from the flow of time, from space-time geometry, then the fundamental quantum units wouldn't be separate particles. They'd be fluctuations of space-time.
So Lang's time slip on large scales could be the macroscopic effect of these fundamental quantum space-time units, Hamada's dark particles, interacting.
It's a very compelling connection. Gravity isn't something separate. It's the weave of time and space itself at the quantum level. And this lets Hamada peer beyond the Planck scale, trans-Planckian physics.
Planck scales. Not the absolute smallest, but where our current physics breaks down.
Right. Try to observe smaller, you need so much energy it creates a tiny black hole, hiding the information. Classically, we're cut off.
But Hamada argues, we're inside the expanded early universe singularity.
That's the radical idea. And echoes of its initial state are in the CMB. The pattern in the CMB matches the large-scale structure of galaxies today,
Implying the universe's structure was laid down right at the beginning.
connecting the largest scales to the smallest. By observing the big universe, we learn about trans-Planckian scales.
And the crucial observation is, the universe is uniform and homogeneous, not singular.
Exactly. Strong evidence that singularities are just mathematical artifacts, not reality.
Which brings us to fluctuating spacetime. The standard idea is spacetime jitters constantly at the quantum level.
But that leads to problems. How do you measure a deforming line with a deforming ruler? Calculations blow up to infinity.
Right. Hamada's take.
The infinities come from missing limits in old theories, assuming flat spacetime, individual gravitons, no overall energy constraint. His new limit. Gravity is quantized only at the scale of the whole universe.
And the total energy of the universe is 0.
Likely 0. Universe from nothing. Positive energy, matter, light, balanced by negative gravitational energy.
Ah, so if the total is 0, the fluctuations, no matter how wild locally, cancel out globally.
Exactly. The total effect sums to 0. No infinite energy left over, no vacuum catastrophe. This is renormalizability. The theory cleans up its own infinities.
First word in the theory's name. Makes sense.
And the observed homogeneity means no pre-existing patterns and the fluctuations got inflated. Fluctuations happen by scale, not shape. Like TV, static space-time bits flickering in and out.
Higher energy, smaller bits, more homogeneity.
Right. And at maximum energy concentration, where a singularity would have been, the region loses meaning for distance and time. It becomes background independent.
Second part of the name. A virtual structure outside normal space and time.
Essentially, yeah, not directly detectable like classical stuff.
And this leads to space-time having different phases, like water.
Exactly. Classical space-time, the rigid elastic state we know, is the low-energy phase. Clear coordinates, physical gravity.
But high-energy space-time.
Not continuous.
Yeah.
No clear coordinates or time, no classical gravity. Energy exists as these scale fluctuations, these dark particles.
And there's a phase transition threshold.
An energy threshold triggers the transition. Hamada calls it the dynamic scale of quantum gravity.
Yeah.
And based on early universe observations, he estimates it's around 107 gigaelectron volts.
Which is lower than Planck energy?
About 100 times less than Planck energy. This is huge. It means no fundamental Planck barrier to understanding quantum gravity.
Gravity loses its physicality before Planck length at a correlation length 100 times bigger.
That's the implication. So gravity isn't quantized into gravitons or loops, but into space-time itself, these fluctuating dark particles. Pure gravitational field energy beyond classical coordinates.
And again, connecting to Ninchi B. Lang, if gravity is the flow of time and space-time itself is the quantum unit, then Lang's time slip is the large-scale view of these quantum time-space units fluctuating.
It fits together conceptually incredibly well. The fabric of reality warping and flowing at the quantum level is gravity.
And these dark particles could solve dark matter.
A compelling solution. Remember, primordial black holes. Tiny black holes formed early on. Good dark matter candidates. Non-baryonic, only gravity interaction.
But Hawking radiation was the problem. They should evaporate too quickly.
Right. Hamada's theory says evaporation stops at the correlation lengths, the size of these dark particles.
Ah, so they don't evaporate away completely?
No. At that tiny scale, it's not a normal event horizon, but a phase transition horizon. The structure is stable, the gravitational potential grows to the correlation length, then drops off.
Making them stable enough to be dark matter.
More stable, yes. They can recapture mass, merge easily with each other. They have zero angular momentum, zero spin, so the Pauli principle doesn't stop them merging.
Unlike photons passing through each other, these merge.
They move to a common center and merge. Hamada suggests vast numbers formed after inflation, became the seeds for structure formation, and are the invisible gravitational energy we call dark matter.
Okay, that's dark matter. What about dark energy and the vacuum catastrophe? That massive mismatch, 120 orders of magnitude.
The biggest blunder in physics, some call it. Hamada's solution goes back to the theory starting from trans-Planckian scales with no cutoffs. And crucially,
total energy of the universe is 0.
Exactly, the perfectly balanced budget. So no matter how you calculate vacuum fluctuations, The correct answer for the total energy contribution in this framework has to be zero.
No huge leftover energy, no catastrophe. Dark energy is just a constant of our universe.
If part of the background value, yes. Not this immense energy density implied by naive quantum field theory.
And this framework also explains the origin of matter and inflation.
It does. Even QED, quantum electrodynamics, has its own high-energy breakdown, the Landau singularity.
Hamada says quantum gravity rescues QED.
Yes. Energy concentration doesn't reach the breakdown scale. It dissolves into space-time, becomes background independent.
Okay, so how do particles appear?
In the very early universe, QED and gravity were perfectly distributed, balanced. As the universe expanded, their force potential grew, peaking sharply at that phase transition point.
The dynamic scale of quantum gravity.
Right. Hamada identifies this as the Big Bang. The sharp increase in forces at that point triggers both of the first particles, photons, gluons, everything in the Standard Model. The visible universe pops into existence.
Wow. So no need for a separate inflaton field or grand unified theories.
It potentially eliminates the need for them. Inflation and the origin of matter become part of the same fundamental process.
And the initial universe just had scalar oscillations, no direction.
Matching observations. All quantum fields interacting balanced out directions. And importantly, the theory respects Lorentz invariance laws are the same for everyone. It quantizes spacetime itself, which starts continuous, so no breakdown at minimum lengths like some theories face.
Okay, practicality, testability. You said it's currently untestable directly.
Energies required are way beyond anything we can build, quadrillions of times higher than the LHC.
So we rely on Occam's razor. Simplest theory wins.
It's a strong guide in theoretical physics. Fewest new assumptions explains the most phenomena.
How does Hamada's theory stack up compared to string theory?
String theory needs maybe 6 or 7 extra dimensions, doubles the known particles, adds new strings, often invokes the anthropic principle. Lots of extra baggage.
Loop quantum gravity.
No extra dimensions or particles, but it introduces discrete space-time at the Planck scale, which can cause its own issues.
And Hamada's theory.
No new dimensions, no new fundamental particles except the dark particle, which is space-time. No new objects. It solves vacuum energy, explains dark matter, matter origin, inflation. By Occam's razor, it looks very strong. It's a really compelling vision. Experimentation is the hurdle, but the elegance and explanatory power are undeniable. It forces us to rethink our starting point.
And this is where it loops back so powerfully to Ninchi B. Lang's ideas, doesn't it? Hamada asks us to start not from our classical world, but from that primordial, hyper-concentrated state.
Exactly. And if Ninchi B. Lang is right, that gravity emerges from the flow of time.
Then Hamada's dark particle, that fluctuating space-time bit, pure gravitational energy, could be the fundamental quantum unit of that temporal flow.
It leads almost directly to the idea of quantum time. If gravity is time curvature and space-time itself is quantized into these dark particles, then time itself must be quantized at the most fundamental level.
Existing as the essence of these fluctuations.
Yeah. This framework really opens the door to a unified field theory. Gravity isn't separate, it's an intrinsic property of quantum spacetime. And since Hamada's theory also births all the other particles and forces from that same state.
It unifies everything. Matter, energy, gravity, all arising from the dynamics of quantum spacetime, where time itself is dynamic and emergent.
That's the breathtaking implication. A truly unified picture. #CAG outro.
Wow. Okay, that is genuinely a lot to take in. From Ninchi B. Lang, PhD's Timescape, showing how our location, our clock speed, shapes our view of the cosmos.
Right down to influencing our perception of cosmic expansion.
To Kenzie Hamada's vision of spacetime itself as this fluctuating quantum entity that is gravity.
We've covered ideas suggesting gravity isn't fundamental, dark energy isn't real in the standard sense, and the Big Bang might be more like a phase transition.
From a balanced, ultra-dense state where quantum time itself is maybe the ultimate driver.
It's humbling, isn't it? But also kind of beautiful. A new picture of the cosmos emerging.
Where our measurements are biased, our clocks aren't average, and what seems fundamental might just emerge from something deeper.
It forces us to see the universe as far more interconnected, more dynamic than we usually think.
So as you go about your day, maybe just pause and think. What other obvious truths, other constants we take for granted, might just be waiting for a different perspective?
How deep do our assumptions run? Questioning those foundations, that's really the heart of science, isn't it?
We really hope you enjoyed this exploration into some pretty deep frontiers of thought.
It certainly challenged us to think about a universe that's, well, constantly surprising us.
If you enjoyed this deep dive, please do consider liking and subscribing wherever you get your deep dives. It really helps others find the show.
And if you feel inclined to support our work, helping us bring these kinds of explorations to you regularly, you can find our GoFundMe page linked in the description.
Every little bit genuinely helps us keep diving deep into these fascinating topics.
Thank you so much for joining us on this journey through the very latest in theoretical physics. We'll see you next time for another deep dive into the mysteries of the universe.